Bismillahirrahmanirrahim. Assalamu alaikum. I am Fakhr Lodi, and this is our 39th lecture of Formal Methods for Software Engineering. We are discussing Z specifications, and in the last lecture, we discussed the process of refinement. So, we are discussing data refinement. Once again, briefly, what is refinement? What we have is we have a Z specification. We want to ultimately take this specification to the implementation stage, that is, we want to have executable code generated out of this specification. So what we do is we take steps and we keep on adding details into the initially vague specifications, initially non-deterministic specifications. Not vague in that sense, because they specify the purpose, they are very clear about what needs to be done, but as far as the implementation is concerned, there are so many different choices open. So what we do is we keep on adding the details, and when we add detail, that means we limit the number of choices available to us. That results in refinement. So, as we keep on refining this thing, we reach a state whereas there is no non-deterministic non-determinism left, and at that point in time, we are able to implement the specification using some programming language. So, last time we saw this process of refinement, and we looked at the mathematical formulation of refinement. We said that, we need to know when a refinement is a proper refinement, that is, it is consistent with our original specification, that is, it does not violate any of the conditions specified there, but it removes certain uncertainty there. So a refinement has to be consistent as well as it has to be correct. So our problem was how to know whether a certain refinement was consistent and correct, and for that we saw mathematical formulation. In that we also looked at what is called the concept of totalization, that is, whenever we have a partial relation, we complete it, we totalize it by adding relations, by adding associations or maps from all the samples that are not mapped onto the range from our domain, and adding one extra sample that defines the undefinedness. If we have a total relation, the mapping is straightforward, and checking for consistency is a straightforward thing. What we do is our refinement should be a subset of our original specification, that is, it may take some of the associations out, and it may take some of the non-deterministic behavior out. But for partial relations, we totalize it, and then we perform the same kind of operation, and we see whether the two are refined, the two are consistent or not. In that, we saw an example of corrupting a bit and then saying that, the first specification that was corrupts to was sort of undeterministic. It had many choices, but then there was a refinement which was a deterministic refinement of the original one, that is, it changed every odd bit from its original, from 0 to 1 and 1 to 0, and that means that it still maintained the property that we specified earlier on, but now it was the behavior was deterministic. Today we shall continue that discussion, and we shall look at a program refinement. A program has a set of statements, is a sequence of statements. That means a sequence of operations that we have. So we have an initial state, we perform, we apply certain operations onto that initial state, and we reach a final state. That is what a program is. That it takes the initial input or whatever we have in the initial state, processes it by performing certain operations onto this input, and gets the final outcome. Now, once again, our initial specifications of the program, they are going to be non-deterministic. And what we want is, we want to have refinement on those steps on the program so that we can have a concrete shape of the program. So let us now go back onto the slide and look at the formulation for refinement of a program. So when we have a program, what does it mean to have a refined version of that program? So let us look at that mathematical formulation. So as I mentioned earlier, a program is a sequence of operations on a data type. An abstract data type X is a tuple in which we have X, which is the data type itself, comma Xi, which is the initial state, Xf, which is the finalization. So initialization and the finalization of X. Then we have a number of operations. So those operations are XOIs. So we can have any number of operations. So each operation is indexed by this I. So XO1, XO2, XO3, and so on and so forth. Those are our operations. So let us now, that was an abstract representation of an abstract data type. Now let us look at a concrete data type. Let's assume that we have this concrete data type D. So we have D, DI, DF, and two operations defined on this abstract data type, and these two operations are DO1 and DO2. And let's assume, we have our program, and this program is DI, which is the initialization part. Then we apply the first operation DO1, then we apply the second operation DO2, and then we apply the finalization, that is DF, and that is our program. So this is the sequence of operations performed on the data type D. So we have this program P on this data type X. That program P is equal to Xi followed by X01 followed by X02 followed by Xf, where this is the generic form, and this is X is the parameter for this program. So we have just started to look at a program. I've shown you a parameterized form of the program, and we said that D was a concrete form. But the important thing to note and remember is that we are talking in terms of the abstract data types. An abstract data type is defined by the state, the initialization process, the finalization process. This could be the constructors and the destructors if we talk about those things in our common object-oriented or abstract data type terminology. And then we have some other operations that we can perform on that particular data type. So we can have any number of operations defined on that data type. So this is what our abstract data type is. So we have the data type, the state, the variables that define the state. So that is what the state is, initialization, finalization, and other operations that we perform in the middle. So a program would be for any data type. Let's just assume that we are working with only one data type. So a program would be initialization of that data type, then performing certain operations. In this example, we saw two operations, D01 and D02, and then the finalization step, and that terminates the program, and that gives us the final state of our program. Now, what we need to do is, if this is a program defined on that data type, abstract data type that we have, we want to convert into a concrete shape. So what we need to do is, we would need to perform refinement on this data type. So what do we need to do? That is what we are going to discuss next. So let me take you back onto the slide and continue that discussion. So if two abstract data types, A and C, use the same index set of their operations, then they will support the same selection of programs. For every program A, for every program PA, there must be a corresponding program PC. What is more, any two programs PA and PC will be comparable since they have the same source and target sets. So the first thing that we are saying here is that, we take two programs, A and C, and we have to determine whether they are a refinement of one another or not. They are comparable or not. We started with, let's say, program A, and we ended up with program C after performing certain steps of refinement. How do we know they are comparable? The first thing is, C must support all the operations that A supported. So the number of operations in C should be equal to the number of operations in A. And all those operations, there should be a one-to-one correspondence between those operations. And if we have a compatible states and we have the compatible operations, then we say that these programs, they are comparable. Then we say that, we have the possibility of one program refining the other program. Now, let us go back and look at it in further detail. So we may find that the effect of PC is defined whenever the effect of PA is defined. We may also find that PC resolves some of the non-determinism present in PA. If this is the case for every choice of P, then it is reasonable to say that C is a refinement of A. Once again, saying the same thing, nothing new here. That is, we say that C removes some of the non-determinism present in A, and if we can say that for every choice of P, then we say that this is a proper refinement operation. So what we do is, in order to check, we have to perform totalization. So we totalize X. So we have this X dot is equal to X inverted T, comma Xi dot, comma Xf dot, comma all the operations. We have the dot defined for all the operations for X. So what we have done here is, we have totalized. We have added that undefined symbol. If this X was a partial relation, so we perform this totalization. And when we perform this totalization, so it is not just that we add this inverted T symbol into that, but remember, all the operations, they are relations. So that means we have to totalize all the operations. We have to perform this totalization on all the operations. And what are the operations? the initialization operation, the finalization operation, and all the operations that we have defined for that data type, they must also be totalized. Since xi and xf are total, the process of totalization does nothing but augment each of them with the set of pairs. That is, we add this inverted T to this data type X, a domain of X, and then we define this relation from inverted T to all the elements in this. So what we have said here is xi and xf, they are total. They are the initial and the finalization operations. And in that particular case, we have the entire domain at our disposal. The rest of the operations, we cannot say the same thing about them. So in this particular case, when we say we are totalizing, since we are totalizing the domain, we are totalizing, I mean, we are saying that some of the operations may be partial. So in order to do that, we need to totalize that. Even if we need to totalize one operation, that means we need to add this inverted T to the domain, and hence we need to make it part of all the operations, even if the other operations, they were total. So this is what we are doing here. So if C is a refinement of A, then P of C dot should be a subset of P of A dot. That means if we have a sequence that is Ci dot followed by COS1 dot followed by COS2 dot and so on and so forth, a COSN dot followed by the last step, that is CF dot, the whole thing should be a subset of this AI dot followed by AOS1 dot followed by AOS2 dot and so on and so forth, AOSN dot followed by AF dot. So if that happens, that means C is a refinement of A. So what we are saying here is that we have the entire sequence, and the entire sequence, we compare the entire sequence, the entire program, with the original program. And so we had the specification for the program. We took certain refinement steps. We started with A. We refined A to C. And in the process, if this whole sequence, we compare it with the new sequence, that is, we get after refining it with C, the two should be comparable, and the sequence that we get should be a subset of the sequence that we have initially. That is, we started with the initial state and we get the final, and performing all the operations after totalization, the final state that we get should be a subset of the final state defined for the original sequence. If that happens, then it is a proper subset. That means it is a proper refinement of the original program. Let us look at one example here. This example is very, very similar to the one that we saw last time. So it uses the same kind of concept and the same example. So it is kind of a continuation of the same example. But, this shows you that, if we have the entire program, then how do we see if it is really a proper refinement or not? So let us look at this example. So we have this program A. We have this data type A, which is a sequence of bits, and we have an action, and we get a sequence of bits. C is also something similar. So in order for these to be comparable, we have to have the same kind of operations defined on it. So C is a sequence of bits. We perform these actions and we get sequence of bits. The action is either yes or no. So both A and C, they are tuples, and the first component, and they have three components. The first component represents the unconsumed part of the input sequence. The second indicates whether or not the next bit must be faithfully reproduced. And the third represents the accumulated output. Like I mentioned a little bit ago, we are kind of continuing with the same example that we used in the last lecture. So here what we are saying is we have the input string of bits, and this action is, it tells us whether the current bit that we are processing must be faithfully copied or not. How do we determine that? Remember, we said two consecutive bits could not be different. So if the previous bit was changed or corrupted, that means the next bit must be the same. That is, the input bit must be copied to the output faithfully. So this is what the action is, yes or no, whether we copy it faithfully or it could be corrupted. So this is what our action is. Now we have the initialization. In this particular case, we have this AI and CI. Both of these, they take two inputs. It is an infix notation we are using here, and it gets a sequence of bits in both cases. And initialization, we say for every bit sequence that is a sequence of bits, we have A, which is defined for data type A, and we have C, which is defined for data type C. We say bit sequence AIA is equivalent to A is equal to bit sequence comma no comma empty, and bit sequence CIC is equivalent to C is equal to bit sequence comma no comma empty. What we are saying here, we are saying that initialization steps for both these cases, for both these data type A and C, they are simply saying that, we have the bit sequence. The bit sequence is simply copied. The action is no. We are not going to do anything with this bit sequence initially, and the output sequence is empty. So the input sequence has everything that we started with, and the output sequence, it has nothing. So remember the tuple, we had the three components. The first one was the unconsumed bit sequence, the second was the action, and the third one was the output sequence. So everything is unconsumed. We have the entire sequence in the first part, that is, nothing has been consumed yet. The action is no, and the output is still empty. So this is what the initialization is. So nothing very special about this specification. Now let us look at the other specifications. The finalization, once again, we have the finalization for A and C, AF and CF, and we say for every bit sequence, we have A in A and C in C, it is defined as the triple. We have AF BS is equivalent to BS is equal to A dot 3, and CF BS is equivalent to BS equal to C dot 3. So in the finalization case, this dot 3 means take the third component of the triple that we had. So we had the bit sequence, the action, and the bit sequence. These are the three components that we have. So A dot 3 means take the third component. C dot 3 means take the third component. And what we are saying is, we simply take the third component, and that is what our answer is. So this is what the finalization is. We are not doing anything with our final state. Once we are at that point, that is the sequence that we get. So these were our two initial, the initialization action and the finalization action. Now let us look at the action itself. So we have this A naught operation. This A naught operation is defined as, we have for every A and A prime, that is the initial state and the final state, we have A naught A prime is equivalent to A prime dot 1 is equal to tail of A dot 1. A dot 2 is equal to yes. That implies that A prime dot 3 is equal to A3, and head of A dot 1 and A prime dot 2 is equal to no. So what we are saying here, we are saying if the second component is yes, that is, if the action is yes, then on the next bit, the action will be no. So if on the current bit, the action is yes, that is, we need to faithfully copy this bit. We cannot corrupt this bit. That means the next bit could be corrupted. Now we have, if A dot 2 is equal to no, then in that particular case, we are saying, A dash dot 3 is equal to A dot 3, and A dash dot 2 will be equal to yes. Or A dash dot 3 is equal to A dot 3 and head of A dot 1, and A dash 2 is equal to no. So once again, what are we saying here? In this particular case, we are saying if we have this no, then next is going to be yes. Two consecutive bits cannot be corrupted. So if one is corrupted, the next is not corrupted. If the current one is not corrupted, then it is possible that the next would be corrupted. So this is what the action is. But you see, in this particular case, we are not saying whether a particular bit will be corrupted. We are saying if the current bit is not corrupted, the next bit may be corrupted. So there is this non-determinism. It could be corrupted, it could stay the same. That means, in our program, for this data type A, we have a degree of uncertainty. And we are going to remove this degree of uncertainty in our refined program and refined operation C naught. So let us look at that and see what happens. So here is our version of this C0 operation. Once again, we have C and C dash, and we say C0 C dash is equivalent to C dash dot 1 is equal to tail of C dot 1. So we are simply looking at the rest of the sequence that we have. C dot 2 is equal to yes, implies C dash dot 3 is equal to C dot 3, and head is C dot 1, and C dash dot 2 is equal to no. And C dot 2 is equal to no implies that C dash dot 3 is equal to C dot 3, and head, we have not head of C dot 1, and C dash dot 2 is equal to yes. So what we have done here, in this particular case, we have taken that non-determinism out. We are saying now the next bit is going to be corrupted. When we use that tilde, that means the next bit is going to be different from the bit in the original sequence. And we have taken that non-determinism out. Now the question is it a proper refinement? Is it consistent with A? For that, we have to look at the entire sequence of program, sequence of operations in that program, and then we see that if it yields a result which is a subset of the state that we got or that we would have got after the applied sequence on data type A. So let us look at that. So what we need to do is we need to say that Ci followed by Cf is a subset of Ai and Af followed by Af. So this is, we must show this. Then we must show that Ci followed by Co followed by Cf is a subset of Ci followed by Ao followed by Af. And we keep on doing this thing. We say Ci followed by Co followed by Co followed by Cf is a subset of Ai followed by Ao followed by Ao followed by Af, and so on and so forth. That is, we start with Ci, we end with Cf, the initialization and the finalization, and between we have 0 or more iterations of this operation that we have defined there. So in the case of C, it is Co. In the case of A, it is Ao. And one thing that we must look at is the number of times this operation is performed in that sequence. On both sides, it should be the same. That is, if for A we have performed it twice, then for B it should be performed twice, and then we should compare the result. If that happens, if we can show that, then this thing reduces to saying that Co is a subset of Ao, and hence it is a refinement of Ao. This is a lengthy step. Obviously, we have to show it for every operation. We have to show it for all combinations of those operations, and we have to show it for any number of operations that we perform there. This is a non-trivial kind of exercise. So what we do is we do what is called simulation. In simulation, we, on the one hand, we have this program A, and on the other hand, we have this program C, data type A and its refined version C, and program based upon A and the program based upon C, and then we simulate, we keep them in parallel, and see if they give us the same results. Before simulation, we need to perform certain operations. The first operation is called lifting. Lifting is a similar operation to totalization, but it is slightly different. It is a subset of totalization. So when we have a partial relation before simulation, we perform lifting. What is lifting? Let us look at this slide. So we augment the state. We augment the state space to allow undefinedness. And it is done to ensure that the definition is applicable to data types with partial operations. As I mentioned earlier, we don't need to totalize. So we have this is called row naught. Note the difference here in the notation. For the totalization, we used the dot filled circle, small circle on top, and here we have the hollow circle, and this is naught. So if we had the relation row, the lifting of row and row was a partial operation, then we have this row dot is a member of X inverted T mapped onto Y inverted T, and this is a one-to-one mapping. And row naught is equal to this row union this inverted T mapped onto every element in the range, including this new element undefined. So this is how it looks like. If we have this language symbols A, B, C, and D, so this is what we have in our domain. Row is A to A to B, B to B, and B to C. In the domain, we are not using C and D. So this is a partial relation. For totalization, what we would have done is we would have included this inverted T, and then we would have mapped C, D, and inverted T to all the elements on the right. That is all the elements A, B, C, D, and inverted T. So we would have a mapping from C to all of them, D to all of them, and inverted T to all of them. But when we are using lifting, we only take this special element, that is this inverted T, and we define a map or an association from inverted T to all the elements in the range. So we will have this inverted T mapped onto A, B, C, D, and inverted T, and we have nothing to do with C and D in our domain. So what we have here is this lifting, as you can see very easily. This was a subset of our original totalization. हमने बाकी एलिमेंट्स को छोड़ दिया जो डोमेन में यूज नहीं हुए थे, but we defined this special symbol undefinedness that is used to define undefinedness, so that whenever we have that kind of situation, we can do something about it. So ये इसमें है. So then what we do is we are ready for simulation. So for simulation, there are a number of things that we need to do. Actually, there are three things. Simulation could be forward or backward. In forward simulation, we move from the starting point and we go to the end point and we simulate things and we see if we get the results, proper results or not. And in backward simulation, obviously, we go from the end to start. So the process is very, very similar. We are only going to look at forward simulation. And what does that mean and how do we perform that? So in forward simulation, we have this Ci dot should be a subset of Ai dot followed by R naught, where R is a relation defined from A to C. The second one is R naught followed by Cf should be a subset of AF. So we are saying here, we are taking care of the initial part and the final part. Then we have in the middle, for each index I, we have R naught followed by COI should be a subset of A naught I followed by R naught. So what does that mean? Let me try to explain that to you. So what is this simulation? We have defined three states: the initial state and the final state, and we have some intermediate states. And for each one of these, we perform certain simulation and we show if it in fact gives us the desired result or not. So what does that mean? Let me try to explain. Initial, we are saying that we are here, starting point. We perform AI and we come to this point. Corresponding to that, we perform CI and we come to this point. Is there a correspondence between these two? Do we have a relation which takes me from AI to CI? So my question was, is this CI? This is my relation. This was R naught that I had. This should be a subset of AI followed by this relation R naught. And of course, I had these totalized forms of these AIs and CIs. If that happens, that means, there is this relation AI and CI, they are related, and, we have a correspondence between these two. Similarly, if we are here just before the finalization and we take this final AF and I come to this point, I should get to the same point by applying this CF operation from this point. And once again, the idea is that do I have this relation defined? So my objective is that I am at this point. From here, I go to the final state after applying this AF. And if I was at that point, CF, application of CF should take me to that point, to the same point. So my question is R naught, from here I come to this point, followed by this CF dot, is it a subset of AF dot. And if I do get that, that means my final states, they are comparable. So I have the condition for my initial state. I have the condition for my final state, and I have simulated. So this is going in that direction from start towards end. From start, I go to this point, and I go to this point, and I have a map defined by this relation R naught. Here, I am just before the final state. I am going into that direction towards my final state. Now I have a situation where I am somewhere in between. So I am at this state, and I apply this operation A naught. And for a corresponding case, I apply this operation C naught. So this is the direction of our operation. I want to find out the correspondence between A naught and C naught. Once again, I have this R naught here, that relation that maps A to C. And the point is that, if I apply A naught from this point, and I go to this point, and then I apply R naught, I should be at this point. Similarly, if I applied R naught and then C naught, I should be at this point. If this path and this path, they are corresponding to each other, then that means it is a proper refinement. So my question is R naught followed by C naught subset of A naught followed by R naught? So this is my intermediate step. So in this particular case, what we have done is we have mapped, we have simulated and mapped initial states to initial states. And we have seen that, we check whether the two correspond to each other or not. The refined state, is it a subset of the original state? Similarly, the final states to final state. We define a mapping function, and that mapping function, of course, has to be a proper mapping, a proper refinement. And once we have shown that the initial states and the final states, they map, then we look at the intermediate steps, and we say if the two, they correspond to each other, that means the programs, they correspond to each other, and hence the second one is a refinement of the first one. It is a consistent refinement of the first one. We can have any number of operations in that. All we have to do is we have to have a proper mapping function, that is that R naught. If we have that mapping function, that means our mapping, our refinement is consistent. If there is no such mapping function, then our refinement is not consistent. So that is what this refinement is all about. This is a long discussion, of course, and we have another kind of refinement that is called the functional refinement, which will take the similar kind of mathematical formulation, and it will take the similar kind of steps. The basic idea behind refinement is that, with each step, you reduce some degree of non-determinism from the original specification. And by reducing this degree of non-determinism, you are also limiting the choices but at the same time, that means you know what exactly needs to be done. So the number of choices are reduced, the flexibility is reduced, but non-determinism is also reduced, and hence you know exactly what needs to be done, and hence you are closer to execution. You can have a compiler which can take it and produce executable code that can be executed. But you need to make sure that each refinement step is a consistent and correct refinement step. So the discussion that we had today revolved around refinement in abstract data types, refinement in programs. And as I said, that the functional refinement is very, very similar. We only saw the data refinement here. We only talked about abstract data types. We did not talk about the functions. The important things in this refinement step were that what we needed to do was we needed to, first of all, look at the operations and determine whether these operations were partial or complete or total. So if the operations were total, we can reduce the degree of uncertainty by taking some of the choices out. So if one element in the domain is mapped onto multiple elements on the range, then we take some of the choices out. So we make it more deterministic. And for a total function, total relation, this is a very simple kind of task. For a partial relation, what we need to do is we need to perform the process of totalization. This totalization is performed because in that particular case, we need to make sure that we do not have the inputs which are not defined. And once we do that, the rest is a straightforward, simple thing. In the next lecture, I will show a complete example. We'll start an example using Z, and we will keep on refining it until we have something very, very close to actual implementation. So till that time, until next lecture, Khuda Hafiz or Assalamu Alaikum.